Hey everyone, welcome to This Explainer. Today, we're diving straight into a problem that literally every tech giant, startup, and developer has to wrestle with: taming the absolute chaos of data management. We're going to start by mastering the incredibly strict, unbreakable rules of traditional databases, and then, well, we're going to flip the script entirely and explore how modern data architectures handle the wild, unstructured information of the modern web. If you've ever wondered how data actually stays organized behind the scenes, you are in exactly the right place.
Okay, let's dive right into this. Here is our roadmap for today. We'll kick things off with identifying your data, move on to fixing database anomalies, tackle multi-value dependencies and the fourth normal form, explore complex data types, and wrap it all up with modern database solutions.
All right, section 1, identifying your data. Every reliable, functional database starts with some incredibly strict rules, right? The absolute baseline here is functional dependency. Think of this using a real-world analogy, like a university student ID card. Knowing a student ID automatically tells us exactly who the student is. The ID essentially determines the student's name. In database terms, if you know one specific attribute, it logically locks in another. It's a one-way street of absolute certainty.
But sometimes one piece of data just isn't quite enough to guarantee uniqueness. That's where a candidate key steps in. A candidate key is the absolute smallest combination of attributes that uniquely identifies every single row in a table. Imagine you're tracking employees and their projects they're working on. An employee ID alone won't work because one person can work on many projects, right? And a project ID alone won't work because a ton of people might be on one project. But combine them together, employee ID plus project ID, and suddenly you've got a unique fingerprint for that specific assignment. You have locked down the row. Moving right along to section 2, fixing database anomalies.
So the crucial point is, what actually happens when we break these golden rules of identification? Well, absolute chaos. We enter the nightmare realm of data anomalies. There are 3 major types that will absolutely ruin your day. First up, the insert anomaly. Imagine trying to add a brand new department to your company's system, but the database flat out won't let you because no employees have been assigned to it yet. Super frustrating, right? Then there's the update anomaly. If a department changes its name, you've got to find and update every single employee's row who works there. Miss even one, and your data is corrupted. Finally, the delete anomaly. If you fire the only employee in a specific department and delete their record, you accidentally wipe the entire department's existence from the database. It's just a total mess of unorganized data.
And these anomalies, they're usually caused by bad dependencies piling up, like a partial dependency. Let's jump back to our ID card analogy for a second. Your student ID already gives us your name. If a database requires a combination of your student ID and a course ID just to figure out your name, well, that's a partial dependency. The course ID adds literally nothing to figuring out who you are. This flaw causes redundant data to just pile up in our tables, wasting space and causing those exact update errors we just talked about. Now, what's really interesting about this next concept is the chain reaction it creates. This is called a transitive dependency. Basically, A determines B and B determines C. For example, your passport number determines your country code, and the country code determines the country name. If you store all of this in one flat table, you are unnecessarily repeating the country name for every single passport holder from that country. This chain causes massive update anomalies. If a country changes its name, you're suddenly updating millions of rows instead of just one. Which brings us to section 3, multi-valued dependencies and 4NF. To actually rescue our systems from this messy data, we bring in the heavy hitters, advanced normal forms. We use these to target really tricky relationships, specifically the multi-valued dependency, or MVD. I want you to pay close attention to this one. This occurs when one attribute determines multiple independent values. Let's ground this in a simple analogy. Imagine a single student. That student can have many hobbies, like reading and swimming. That same student can also have many certificates, like first aid and CPR. Now, the hobbies have absolutely nothing to do with the certificates, right? They are completely independent of each other. Yet, they are both determined by who the student is. If you try to shove all of this independent information into one giant table, it's a disaster. Think about the before scenario. The data just repeats infinitely. To list 2 hobbies and 2 certificates, the database forces you to create 4 rows of mixed and matched duplicates. It wastes massive storage space. But then, look at the after scenario. By applying the rule of separation, we tame the MVD.
We separate the independent information into smaller, dedicated tables. One for hobbies, one for certificates. The result? Zero repetition and super easy updates. Once you successfully eliminate those unwanted multi-value dependencies, your database hits what we call the fourth normal form, or 4NF. It's honestly a lot like organizing a really messy bookshelf. Before 4NF, you've got novels, textbooks, and magazines all stacked haphazardly on top of each other. Finding anything is basically impossible. Applying 4NF is simply the act of putting the books on one dedicated shelf and the magazines on another. Suddenly, everything becomes clear, structured, and perfectly organized.
Okay, so we've spent this whole time perfecting the clean, strict rows and columns world of relational databases. But here is the plot twist. What if your data completely refuses to fit into neat little rows and columns? What then?
Let's explore that in Section 4, Complex Data Types. Welcome to the messy, complex, and honestly incredibly exciting reality of the modern web. Because as technology evolved, so did the stuff we actually needed to store. We're not just storing names and IDs anymore. Just contrast these two concepts for a second. On one hand, we have textual data. This isn't just a short string of characters. We're talking about a massive digital library of entire books, emails, customer reviews, and dense reports. You obviously can't just cram the whole book of Moby Dick into a tiny Excel cell. On the other hand, we have spatial data. This is the backbone of things like Google Maps or Uber. It's a highly complex geographic information system full of coordinates, shifting locations, and mapping geometries. Traditional tables simply choke when they try to process this natively. And then, of course, we have semi-structured data. Think of your JSON or XML formats. It's literally like a shared notebook where everyone writes a little bit differently, but they still use sticky notes to label things. It has organization, yes, but it completely ignores the whole concept of fixed columns and rows. One record might have 3 fields, and the very next record might have 50.
Finally, let's wrap up with Section 5, Modern Database Solutions.
Here's the thing. You absolutely cannot force this modern, complex data into those old engines. It just won't work. You need specialized engines built from the ground up to power the big data era. And this brilliantly illustrates how our tools have evolved. If you're building a social network like Facebook, you don't use a table. You use a graph database, which stores data as nodes and relationships, instantly connecting friends of friends. If you're managing millions of IoT devices or traffic sensors, you use a streaming database to process that nonstop fire hose of data in real time. And when your dataset is simply too massive for any one computer, you use distributed models like MapReduce. It chops the data into pieces, maps them across thousands of servers, and then reduces them down into a single, cohesive answer. It's a real game changer.
We've journeyed all the way from the strict mathematical rules of fourth normal form straight into the distributed computing of the modern web. The chaos of data can be tamed, for sure, but only if you use the right tool. So I'll leave you with this. Next time you're analyzing a system or spotching out a brand new app, look closely at the information you have and ask yourself, what database does your data actually need? Thanks for joining me on this explainer, and keep building smart systems.